Did you know that in many farming regions, 1 out of every 5 water wells is silently poisoned with nitrate levels above the 50 milligrams L safety limit? You can't see it, you can't smell it, and you certainly can't hear it coming. Contamination moves underground, invisible to the eye, until crops begin to fail or local clinics notice a sudden spike in illnesses. This is contamination without a sound. Unlike a surface spill, underground contaminants travel slowly and unpredictably. A pesticide applied to a field this year might not show up in a drinking well for several years, depending on the soil and rock it passes through. In sandy or gravelly soils, a contaminant plume can move quickly. But in dense clay, it might barely move at all. As it travels, the plume also spreads out, diluting slightly but covering a wider area. Some chemicals stick to soil particles, slowing them down even more. This delayed, complex movement is why groundwater contamination is such a deceptive threat. So where does it all come from? The primary sources are chemicals, salts, and sewage. In agriculture, nitrogen fertilizers are a major culprit. Excess nitrate is highly soluble and moves easily with water into the aquifer. In California's Central Valley, some wells show nitrate concentrations over 80 milligrams L. This not only makes the water unsafe for infants, but can also damage crop growth. Pesticides are another concern. While many break down, their byproducts can be even more mobile and toxic. Next are septic systems and sewage. Many rural and suburban areas rely on septic tanks, which can leak over time, releasing a cocktail of bacteria, ammonium, and eventually nitrate. In coastal areas with poor sewage infrastructure, this leakage contributes to rising salinity in the groundwater. Speaking of salt, seawater intrusion is a growing problem in coastal regions. When we pump too much fresh water from the ground, we lowered the water table, allowing denser salt water from the ocean to push inland. In parts of Florida, overpumping has caused the saltwater wedge to advance by meters every year, turning fresh wells brackish. Finally, there are industrial sites and landfills. Leaks of chemicals like chlorinated solvents can create dense, long-lasting pools of contamination deep underground. And while modern landfills have protective liners, older unlined dumps continue to leach a toxic mix of heavy metals and organic acids into the soil. So, how do we find something that's invisible? We've moved beyond just taking water samples. Modern diagnostics use a combination of geophysics, advanced chemistry, and real-time sensors. Electrical resistivity tomography, or ERT, can map underground plumes by measuring how electricity travels through the soil. Salty water, for example, is much more conductive. We also use isotopic tracers. By analyzing the nitrogen and oxygen isotopes in nitrate, we can tell if it came from synthetic fertilizer or from animal manure and sewage. Continuous sensors placed in wells now give us real-time data, sending an early warning if a spike in contaminants occurs after a heavy rain. This combination of tools allows us to build a detailed 3D model of the problem underground. Once we've found the contamination, how do we clean it up? The approach depends on the contaminant and the geology. The classic method is pump and treat, where we pump out the tainted water, clean it on the surface using filters or biological reactors, and then put it back. It's effective, but it's also slow and energy intensive, sometimes taking decades. A more advanced technique is in situ remediation. Here, we inject nutrients like vegetable oil into the ground to stimulate naturally occurring microbes that can break down contaminants. In one project, this method dropped nitrate levels from 60 mg L2 below 10 mg L in just 18 months. For a more passive solution, we can install a permeable reactive barrier, essentially an underground wall built with materials that neutralize contaminants as groundwater flows through. A wall made of zero-valent iron, for instance, can effectively destroy chlorinated solvents. To combat seawater intrusion, engineers build hydraulic barriers by injecting fresh water to hold back the saltwater wedge. And sometimes, if a plume is stable and breaking down on its own, the best option is monitored natural attenuation, which means we watch it closely to ensure it doesn't spread. Of course, cleaning up is expensive and difficult. Prevention is always the better strategy. This means smarter farming practices, like using less fertilizer and creating buffer zones around sensitive areas. It means upgrading old septic systems and expanding modern sewer networks. It involves stricter regulations for industrial sites and better containment for landfills. And crucially, it requires robust monitoring and making that data available to the public. When communities are informed, they can become powerful advocates for protecting their water. Citizen science programs, where residents use simple test strips to monitor local wells, have successfully pushed for cleanup actions. Ultimately, contamination is a complex problem, often with multiple sources mixing together. The future of groundwater management lies in combining higher resolution monitoring with targeted, efficient cleanup technologies. But containment and cleanup are only half the battle. The most sustainable strategy is to pair remediation with proactive water replenishment. Thank you for watching. If you found this helpful, please like this video and subscribe for more content.